I'll start out. Hey, good morning, everyone. I'll start out with a simple question about the wave glider. No, sorry, the sail.
The sail drone?
Yes, the sail drone. How much does the wind availability and direction affect your ability to go where you want?
Sure. So sail drone, I want to be clear that this is their product. This is the company's product. But they have an automated tacking algorithm. So essentially you set waypoints and it will tack to get there. Depending upon the wind strength, it will tell you how long it takes to get there. Depending upon how closely you want to keep to a given cruise track between those two waypoints will depend on how long it takes to get there. But waypoint tracking is not a problem based on wind direction.
I have a question for Oscar. You talked about automated glider missions and taking humans out of the loop, and I'm curious what your thinking is on how far we can take this kind of taking humans out of the loop, like all the way to data analysis and massive data set analysis. Maybe even write our papers for us.
We were joking at coffee, but there is a human language autonomy group in Central Florida that's actually working on that. So the data reports and progress reports is probably 10 years out. But I think for us, we've been thinking it more along how do you make it easier to have tons of these systems out there and not having your technicians die. So like one example would be you want to do a cross-shore transect and you give it a waypoint, but you don't really care where at the shelf edge it goes, and it can look at its own current data and save 10% of its battery if it changes its position 10. So that's sort of the level we've been doing it right now.
I had another practical question about the sail drone. Sorry if I missed this, but if I understood right, the wind power is used for the propulsion and solar for the sensors.
Correct.
There's a really impressive sensor payload capability. Is power limiting, and how much is available for that?
So we consider the basic power draw on the sail drone to include the the MET package and the physical sensors. So we never really cycle those, they're always on. There are 3 high-powered sets of sensors: the acoustics, the chemical sensors like the MAP-CO2 system, and the ADCP. Right now, we can run the full suite of MET and physical sensors and any 2 of the high-powered sets of sensors. So whether that's acoustics in MAP-CO2 or ADCP in MAP-CO2, that's my favorite configuration. At the same time, but we can't do all 3 at the same time. Does that help answer your question?
Yeah, I guess so. And if you have a week of clouds, you have to turn everything off, or?
Cloudiness has not been a really big challenge for us so far. Like I said, we deployed in the Bering Sea, which is notoriously gray and stormy. So even running the MET package, the acoustics by itself, so only 1 set of the high power sensors, and the physical sensors, we didn't drop below 60% battery ever last year across a 3-month mission. So we're really not concerned about solar until the light starts to die off in the wintertime.
So, hi there, this is Patty Matrai. Then this is a question for everybody up front, and actually probably many of us back here, certainly for myself as well. As Craig knows, but others in here may not know, we design, build, and deploy autonomous systems which are ice tethered. And so the question is one, and we've been doing this for 9 years, it's just not this community. And the question that we struggle with, and the one that I started here, has to do with calibration and validation. And to what extent should we be making those data available to everybody else? Because usually we use them for our own systems, we publish the finalized data, it's available for everybody. But then whoever then gets a new system has to reinvent that wheel for their own location and question. So to what extent should we go one step further and actually provides some of those data so that we don't have to reinvent the wheel? And I haven't been able to answer that question to myself. So I would like to see what your thoughts are.
I could start by, so with Nabo 8, right, we tried to publish all that very carefully through Bigo Demo, documented reports, both the methodology and the raw data and the products. And I think something like that would be incredibly valuable, because you're exactly right, the kinds of things you'd like to have as a library that you could go to and look things up.
Yes.
We should.
Yeah, but you have to be really careful, because there's 8.5 million data points, and if you're going to put garbage out there, you know, you have to, and it's not a trivial process to quality control those large data sets, and I'm not sure how many people validate them well. So I think developing the process for how you do that and sharing that would be extremely valuable.
I'll go one step into left field and say that I always want onboard calibration. Like the MAP CO2 system runs its own standards, so I don't have to go take a bottle sample if I don't want to. It's not ideal not to do that, but I can still use the data and have some estimate of the error qualification on it. And that's true for some of the other sensors as well. Obviously, that's not possible for everything that we work with, and would be a huge power draw and space and payload draw. So figuring out how to conduct those calibrations, especially when you're under the ice. If the goal is to eventually take a glider under the ice itself without a ship being in that area, how do you calibrate that, period? Are we going to have to design an observing system that includes fixed calibration points that you can just bypass? I could geek out about that with you for several hours.
Hi, this is Jessica Liu. So I did some work with an in situ zooplankton imaging system, and my experiences were that we had such a deluge of data that it was often really difficult to process and then interpret the observations that we had. And my observation with the rate of technological increase is that we have all this big data without a commensurate conceptual or theoretical framework with which to interpret some of the data that we acquire. And a lot of the theory that we have is, decades old. So I'm wondering if you could comment a little bit, this is kind of a broader question for the whole group, on some of those conceptual developments or theoretical developments, and maybe some of the need for that too.
I think that's what Carl was telling about in that quote that and I agree with you. I think the pace of technology has exceeded our scientific capability of dealing with that. But that's about all I can tell you. I don't know that I have a lot of good ideas of how to improve on that, but maybe somebody else does.
Yeah, I agree with the conceptual developments too. I mean, and that some of the conceptual models are really old, but I think for the first time with this high resolution, we actually have a way to test these old hypotheses. And some may still be valid. I mean, it came up a few times that patchiness is really important. We know for a fact that if we feed organisms, especially let's say fish larvae, at the average food concentration, they would all be dead. There has to be patches, and we can resolve these patch structures temporally and spatially now. And we can test something like the last stable ocean hypothesis, or something like that, or Cushing's match-mismatch hypothesis, temporally speaking. So that's for the first time it's possible, and we can do that. So yeah, but I think the development of new concepts will go hand in hand with the discovery of new features and behaviors, as we've seen.
Yeah, my one thought is if you have, with a lot of these systems and it's open data, you can democratize oceanography. Historically, right, it's the person who's on the ship who has access to the data and knows the story, and it's a pretty small subsection of the science community. And so if we develop tools and metadata and all those things, maybe we can get more eyes looking at the problem and develop some of those new conceptual frameworks.
Sorry, I do have a comment though to add, because something like, inline digital holography, PIV, I mean, these are actually techniques that have been around for quite some time. So in the engineering literature, there have been massive improvements in terms of, trying to speed up the processing of data, miniaturize systems and things like that. I think really what I think this community has really been kind of stuck on is, how do you then automate the identification of whatever it is you're looking at? And so, with machine learning algorithms, there's plenty of developments I know in this community. I mean, we're getting there. But, it's interesting how there's very different groups all working towards essentially the same solution, or, that you talked about.
Hi. Oh, yeah, it's on. I had a question about the sail drone and whether or not it could handle the Southern Ocean during perhaps the winter.
Speaking for the company again. So Sail Drone right now is working on a mission where they have 3 boats that are trying to circumnavigate the globe and make it through all of the different oceans. It's still ongoing at this point. One boat had some structural problems. It was related to a defect in assembly and manufacture, so it dropped out. And then they got most of the way around the globe from San Francisco, but one of the boats disappeared around Cape Horn, which you can imagine why that might have happened. A really violent area, so if we're talking the Southern Ocean in wintertime, maybe the boats aren't quite equipped to handle that sea state yet, but I would emphasize that that's a yet.
Hi, Debbie Steinberg. I have a question about the deep PIV, and I was wondering, does the organism need to be pretty stationary for you to make these measurements? Like, could you do this on a, siphonophore pumping water through its swimming bells, or any?
Yeah. Well, so when I started doing these flow measurements, I started actually looking at jellyfish as a model for biological propulsion. And the biggest challenge when you're using, this device or this instrument is making sure you're on a platform that's stable, right? Not, like motionless with respect to what it is you're trying to measure. And so that's been kind of a challenge when you're trying to communicate that with, let's say, the ROV pilots, because the instinct is to follow, the target, whereas I'm then instructing them to hold position and then just allow the animal to swim through it. So we have done some work on siphs. They're, fast. Calicopherans seem to be a little bit easier to work with, partly because, they're stationary to begin with. We've also done this with jellies, passive phaids when they're generating their feeding currents because they're stationary. So anyways, there's plenty of questions that we can address with the instrument in its current form now. But I do believe that, with miniaturization and then also carefully selecting future platforms like Lagrangian floats, let's say, you can do these kinds of measurements to look at more physical flows or, particle settling and stuff like that.
Thank you.
Yeah.
Ken Bissler, and I guess it's a similar question. We saw a lot of pictures of beautiful particles and animals, but can we see settling velocities? Can we see relative differences in sinking speed? How close are we to doing that and having a calibration even to do that?
Right, so I believe it was like my second to last slide. I showed some of just raw data that we'd collected with siphon exhaust flows with sponges. And so you can see very clearly there that, we have really sufficient particle densities to do, the traditional particle image velocimetry analysis. And so in those, situations, we're on the bottom, we're stationary, and the signal to noise ratio between, our constrained motion versus what the particles are doing is more than sufficient. But I'm really not, and this is maybe a question to the float community, how Lagrangian is your float? And and then that's something too we could also understand or use this instrument to really evaluate. And then in terms of validation, I did mention we have the vortex ring generator that we used in early deployments with the intention of essentially comparing a classical physical flow that's, can easily be replicated in a laboratory environment in situ. So these are all things that we're thinking about and being concerned about. But again, the stability of the platform is extremely important.
Hi, this is Jamie Palter. Thanks for, it's great to hear these like futuristic talks, which are now part of our present, which is really cool. My question is about a platform that hasn't come up, but I think might bridge some of these gaps in that it collects basin scale measurements and long time series, which are ships of opportunity, like the container vessel Oleander that goes from New Jersey to Bermuda every week, and which collects like ADCP data for the physical oceanography community, but it's backscatter, which can be used for biology as well. But it's a bulk characteristic of the ecosystem. And I wonder if you would have ideas about pairing some of these autonomous vehicles with that on an episodic basis to have something that gives species level or ecosystem level data to pair with the bulk characteristics of the ecosystem collected by those ships.
Some of those ships have been equipped with continuous plankton recorders. So that data set is growing, I think. We've been thinking about, well, how can we make it new or smaller? Because that's a pretty ingenious device. I mean, it's got this little roller of material that it collects, and can you actually miniaturize that and put it on other things? But the ships, there is a growing, I think, effort on that front of using the ships to collect ecosystem information.
Mary Jo Richardson from Texas A&M. The talks were outstanding. All of you did a fantastic job. So all of us in the room know that NSF has invested very heavily with an MREFC infrastructure of the OOI. How does what you've talked about today fit in with OOI?
I guess I'll answer that one. I actually think when you compete for an MREFC, you're supposed to be pushing the envelope of engineering plus the science. And if you look at some of the challenges of OOI, it's the diversity of sensors. Argo did an amazing job, and they focused on some core measurements. While if you look at the sensor profile of 600 different types of sensors, has been a huge challenge. But it's actually central to a lot of the things you saw today, which is sensors come online and we have a diversity of them. How do we handle it? Because often getting a driver and getting the data processed and out is the fundamental thing that leads to a lag before it's available in publication. And I still think it's a work in progress. And so the investment there is struggling with the same process we'll see with a lot of these networks when they're operating in a sustained way. We're used to operating them for like a 2-week experiment, a 3-week experiment. That's very different than continuous long term.
I have a question for you guys. A lot of the work, especially on networks of things, it comes from labs that have decades of experience and mistakes, and fixing mistakes, and all that sort of thing. And and I'm just trying to think how to get the tools into the hands of everybody. And for ships, we have UNOLs. And, you write a proposal to NSF, you can get some time on that and access. How close are we to implement? Is that an implementable vision? We do it a little bit with the Deep Submergence Lab. We do it a lot with the Deep Submergence Lab. There's a lot of examples. Are we mature enough to be thinking about this? Just a general question.
The setup. No, so earlier this year, the kind of autonomous platforms community got together in San Diego, roughly 13 years after the first such gathering. And this was the subject of quite a bit of discussion, right? How to democratize the access to the technologies. The barriers to some are fairly low, right? Float technologies are the standard profiling floats are relatively easy to deploy. probably the closest thing we have to an appliance. You could argue that with glider community, we're still quite a long way behind, right? The reliability and usage barriers are quite high. And so the current mode is that you befriend somebody that does this and learn how to do it, which is not a particularly good way to spread the technology. So different models have come up, right? There are models, that's one model. Another model is a facility, whether it's a Mars-like facility, which exists in the UK for autonomous platforms, where they offer a service, right? If you're funded, you get access to these vehicles and people that know how to use them. Hybrid models of doing that, along with individual groups still doing development. It would be very interesting to get input from the community about this, because I think there's going to be a push, right? We're trying to push to do something that will broaden access, and the something depends on what the community at large thinks would be useful, where we try to push it.
But I do think, it's come a long way from the time when there was only 1 or 2 labs that could run gliders. I mean, Oscar's point earlier. So it's a slow process. The floats are getting out there. The problem is that with some of these things, the technology is not quite mature enough to transfer. And so it's still at a point where it doesn't make, and that's sort of a challenge to all of these observatories, is the fact that, something we talked about earlier, is how fast the technology is moving. And so you can get obsolete very quickly. You invest in a big infrastructure.
Yeah. Well, I mean, I think, we operate, for those of you who don't know, we operate a facility here. We run Alvin, the human occupied submersible, the ROV Jason, and the AUV Sentry. And, we've been able to put that on a stable, footing in terms of personnel and delivering well-described products and services. And to the extent that people write proposals, they, just like for a vessel, they have an opportunity to know what it is they're going to get, and then a lot of the financial aspects of that and all of the technical operational aspects are not the burden of the principal investigator. And so you could think about, and I think that's to the extent gliders are definitely moving in that direction, where people with tough problems can concentrate on their expertise, and those details will be taken care of. So I think that needs to be extended. I like to point out another possible way that technology can get kind of amplified. If you're familiar with the Open ROV project, they have this small, low-cost, almost hobby ROVs. They did like a Kickstarter, and they tried to get, $50,000. They got $800,000 with people putting up advance orders for these things. So if someone can figure out how to mobilize that community of enthusiastic, people who are putting out their own money to buy these platforms. Now, I haven't quite imagined the resonant problem where, if I had access to 2,000, hobby class ROVs, how I could do something really important. But I think it's only a matter of time before somebody figures that out. They've got this active community of passionate, practitioners, if you will, and mostly at their own expense and their own time, out there getting data for them. I mean, you see it in astronomy, you see it in
robotics.
Robotics, yeah. So I think it's just waiting for those pieces to really come together. If someone can figure out what to do with those, 1,000 of those low-cost ROVs, with each operated by some incredibly enthusiastic, passionate person waiting for someone to direct them to contribute to a big science question, they would leave it.
No, I agree. You have the democratization comes from how cheap electronic components get. And like just the example that I gave for this miniature, I had a fairly beefy recording system, but this chip records that people put on drones because they have these competitions and they want to film each other flying. That democratizes a lot of things, and we have people, undergraduate students and graduate students at ODU, build great CTDs from scratch with fluorometers and all sorts of optical devices, just with a shoestring budget to observe variability in creeks on the marshes and stuff. So there's that aspect of that electronics components get cheaper, and kids get smarter at robotics too. So, yeah.
Oops, this is Barney Balch. Optimal sampling of any phenomenon, whether it's whales or phytoplankton, requires a good idea of spatial scaling for where you want you put your instruments. How good is the robotic behavior now for swarming or for maintaining gliders at a constant distance? How far has that advanced over the past few years? Maybe that's for Oscar.
It has improved. Like a good example is those hybrid gliders now with a propeller you turn on and off if you need to give it a push. And Craig showed the example of one glider which couldn't keep up with some of the drifting things. I think right now the issue is we're still learning how to put those things together. And so like with the penguin example, it's the data lag of getting where they are into a system for us to use quick enough, so it varies a lot system to system. So I think we're doing the experiments right now.
So one thing to keep in mind, there's a large community that thinks about autonomy and behaviors for how you direct these vehicles and how you manage swarms and how you vector them in to do different things. And that's a very active area of research. And there's a community that's been doing platforms in the ocean, and that's been a fairly active area. And the space where those two meet is been relatively narrow to date, right? Because the things that the people are theorizing how to run the platforms are doing and aren't quite things that we can execute at the more right. For instance, we don't typically run experiments with large numbers of platforms. Or if you look at most of the deployments are in onesies and twosies or a few. We've had a few deployments of a dozen vehicles, but not very many. That's pretty rare. And the vehicle behavior is Oscar said, that driving a glider isn't like driving a car. It's more like driving a car with a really loose steering wheel, right? You kind of get vaguely where you want to go, but directing it to an exact place is difficult.
And are gliders talking to each other?
No, so that's an interesting point. We call them autonomous platforms. They're actually sort of high latency remote control platforms at the moment, for the most part. Right, some of the work that we've done under the ice and that, different, there are some instances where we're starting to exhibit autonomy, but largely they're piloted and the brains are on shore. We've had some luck doing automated patterns based on that, but the vehicles are still not, by and large, making their own decisions.
Yeah, and I think in terms of, what fields we can look to in terms of forwarding that kind of interaction between multiple vehicles, I think, the drone space, they're getting really far. I mean, you look at now Amazon's, they've got a proposed hive where you've got multiple UAVs, docking and leaving. And so I think we'll look to those communities, and I think then we can take some of those lessons and apply them in underwater applications.
Okay, we're going to have to close this now. I'd like everybody to want to thank the panelists and speakers today.